Picture every star in the sky. Now picture the planets circling each one. Dozens, maybe hundreds of billions of them scattered across the dark. As far as we know, almost every single one is just rock or gas or ice. Silent, empty, dead. So what did this one world do differently? That question is not really about astronomy. It's about you, because you are sitting here, reading light off a screen, breathing air, thinking thoughts, and none of that was guaranteed. Think of it like a lock with a dozen tumblers, and every single one had to click into place, in order, just once, for this moment to exist. We are not going to rush past that chain. We're going to walk every link of it in full because it deserves the time. So let's build a living world, not metaphorically, literally from scratch, like following a recipe, checking off requirements one by one, the way you'd assemble something complicated on a workbench. The first question is the simplest. What kind of galaxy could even host a place like this? Not every galaxy will do. Too close to the crowded center, and you're bathed in radiation, swept through by other stars. Your orbit destabilized by gravitational chaos. Too far out toward the sparse edges, and there simply aren't enough heavy elements, carbon, oxygen, iron, the leftover dust of dead stars that any rocky planet, let alone any body, is built from. So the address has to be just right. A galactic habitable zone, astronomers call it, a modest, unglamorous ring partway between the blazing core and the barren outskirts. Most of any given galaxy fails this test. Ours, the Milky Way, with something like 200 billion stars scattered through it, happens to have a livable neighborhood. That's filter 1, cleared. Now, what kind of star? Because most stars are wrong for this too. Many are too small and dim, their habitable warmth pulled in so close that a planet gets tidally locked, one face frozen, one face scorched. Others are too massive, burning fast and violent, and dying within a few 100 million years, nowhere near enough time for anything to get started. You need something steadier, a star like our Sun, a G-type star, stable, middle-aged, patient. And those make up only about 7% of all the stars out there. So what if the star flares, even a good one, in a bad mood? A single violent burst can strip an atmosphere clean off a nearby world in geological moments. Most stars fail this filter too, one way or another. But say you find a calm one. Now, where do you put the planet around it? This is the part people have heard of. The habitable zone, the narrow band of distance where it's warm enough for water to stay liquid, but cool enough that it doesn't boil away into space. Too close, and you get a hothouse, a runaway greenhouse, thick clouds, and lead-melting heat. Too far, and every ocean freezes solid, forever. That band is thinner than it sounds. Move a planet just a little closer or a little farther, and the whole equation collapses. Most planets simply don't land inside it. But say, by chance, this one does. Now, how big should it even be? Too small, like Mars, and the planet can't hold on to an atmosphere at all. The gravity's too weak, and the air just leaks away into space over time. Too large, like Neptune, and the planet pulls in a crushing shroud of hydrogen and helium, a thick gas envelope with no solid surface to speak of. You need something in between, big enough to keep a blanket of air, small enough that the pressure doesn't flatten you. It's a narrow window, and most planets overshoot it in one direction or the other. But say this one, somehow, lands right in the middle. Now it needs a moon. Without a large stabilizing moon, a planet's tilt can wander chaotically over millions of years, swinging from no seasons at all to wild extremes, unpredictably, again and again. That kind of chaos makes it very hard for any climate to hold steady long enough for anything complex to take root. Our moon, unusually large for a planet our size, holds Earth's tilt steady within a couple of degrees, like a spinning top with a weight in exactly the right place. Most rocky planets don't get a moon like that. This one did. Now zoom out further to the edge of the system, because this world needs a guardian too, far out in the dark. A large outer planet, a gas giant in a wide orbit, acts like a gravitational shield, pulling in or flinging away comets and asteroids that would otherwise rain down on the inner planets. Without one, the bombardment never really stops. Impacts violent and frequent enough to sterilize a surface again and again, resetting the clock before life ever gets a foothold. Our solar system has one, sitting in almost exactly the right place, doing exactly that job for billions of years. Most systems we've found show no clear sign of a guardian like it. Now, last of the 7, go back down, beneath the surface. A planet needs a churning, molten core, because that churn generates a magnetic field, an invisible shield that deflects the solar wind, the constant stream of charged particles a star throws off, which would otherwise strip an atmosphere away over time. That same churning also recycles carbon between the surface and the interior, keeping the climate in balance across hundreds of millions of years instead of drifting into permanent ice or permanent furnace. Without that inner engine, a planet slowly loses both its air and its thermostat. Ours has been running for 4.5 billion years without stopping. So, a safe galaxy, a stable star, the narrow orbit, the right size, a steady moon, a distant guardian, a churning core, 7 filters, and losing any single one is enough to end the story before it starts. So, what did this one world do differently? It didn't do anything at first. It just happened to pass through all 7, a chain of odds compounding on top of each other, filter after filter, no single miracle, just an accumulation of very narrow doors, all standing open at once. And even that isn't the hardest part. Because after all 7 filters, you still only have chemistry. You have water and carbon and warmth, and none of that is alive yet. Somewhere, in some pool or vent or shallow sea, non-living molecules had to arrange themselves into something that could copy itself, feed itself, and change over time, the very first living cell. We still don't fully understand how that step happens, and by most measures, it's a bigger leap than all 7 filters combined. And even after that, after life exists at all, there's a second leap, arguably steeper still. For most of Earth's history, life was simple. Single cells, drifting alone for billions of years, with nothing that could be called a body, a brain, or an eye. The jump to complex life, cells cooperating, specializing, becoming something like a plant or an animal, happened only once that we know of, roughly 2 billion years ago, and it may be the rarest event in this entire chain. We have looked, by the way. In 2025, scientists thought they might have found a hint of biology on a distant world called K2-18b, a possible biosignature drifting in its atmosphere, 124 light-years away. Follow-up observations couldn't confirm it. The signal faded back into noise, and the world, most likely, is not an Earth at all, but something stranger. A thick, hydrogen-shrouded ocean planet unlike anything in our own solar system. So here is the full accounting, the one you didn't have at the start. A safe galaxy, a stable star, the narrow orbit, the right size, the steady moon, the distant guardian, the churning core, then chemistry becoming life, then simple life becoming complex life. 9 near-impossible doors, one after another, and every single one of them, as far as we can prove, opened here. And only here. We genuinely don't know if that makes life rare in the universe or secretly common. Maybe there are 10,000 living worlds quietly turning in the dark right now, each one having passed through its own version of this same chain. Or maybe there is only one. Both answers, if you actually sit with them, are staggering. What we do know, with total certainty, is smaller than that question, and somehow bigger. There is exactly one place, out of everything we have ever looked at, where we know for sure the lights came on. Keep pulling back, past the moon, past the sun, past the orbits of every other planet in this system, out until the sun itself is just one point of light among the others. Somewhere in that scatter of stars is the one you started with, the one world out of everything we can see, where a safe galaxy, a stable star, a narrow orbit, a sturdy size, a steady moon, a distant guardian, and a churning core all lined up. And then chemistry became life, and life became something that could wonder about its own existence. If a message ever needed sending across that kind of distance, a signal worth trusting, built to last, carrying something true across all that empty space, it would need exactly the same qualities this whole story has been about: care, precision, patience with the long odds. That's the same spirit behind the research and fact-checking that goes into every one of these episodes, and behind the people who choose to support that work so it can keep going. Because from out here, at the edge of the frame, it's not a planet anymore. It's a point, pale, blue, with the faintest edge of green if you know to look for it. A small blue dot holding everything and everyone you have ever known. The one place, as far as we can tell, where the universe woke up enough to look back at itself. That's the whole story, and you're standing on it.